Hi everyone, we're going to go ahead and start on simple harmonic motion. Simple harmonic motion is a nice precursor to waves because it gets us familiar with things that vibrate or oscillate at a regular time interval. And things that vibrate or oscillate back and forth through the same path at a regular time interval are called periodic. And a good example of this is a pendulum. If you pull a pendulum to one side, it'll swing back and forth, back and forth, back and forth, with approximately the same side-to-side motion with the same amount of time for each complete swing. So that's periodic motion. Another thing you could do would be to hang a mass on the end of a spring and let that vibrate up and down. That would also be periodic motion. So we're going to investigate this periodic motion. What makes it simple harmonic motion? In simple harmonic motion, there is a restoring force that is directly proportional to the distance that this system is pulled from equilibrium. Now remember, equilibrium means unchanging. So a system in equilibrium would be like this pendulum right at the bottom, because gravity is pulling straight down, the tension in the string is pulling straight up. Those two things exactly balance each other. The net force is zero, the acceleration is zero, the velocity is zero. Now as soon as we pull a pendulum to the side, then gravity pulls down this way. Tension pulls this way, and that component of tension actually has a restoring force. It tries to pull it this direction to put it back in equilibrium. Same with the spring. If we have this here, gravity's pulling down, the spring is pulling up. If we push this one direction or another, then the spring is either going to try to pull this thing up, or gravity's going to pull it down and move it back to its equilibrium position. So in simple harmonic motion, there is a restoring force directly proportional to displacement from equilibrium. Now, I probably won't ask you that, but that is the definition. And it turns out a pendulum is not quite simple harmonic motion, but it's close enough that we're going to go with it. And that's another benefit of simple harmonic motion. A lot of vibrations and oscillations, even though they're not exactly simple harmonic motion, can be modeled with simple harmonic motion. So this is a powerful, a useful model for motion. Now there's a few more terms I want you to think about, to be familiar with. Remember, period. We said a motion is periodic. Period, that is the time for one complete oscillation. Time for one complete vibration or oscillation or back and forth motion. So if we had our spring here and a mass hanging on the end of it here, and it was moving up and down between these 2 points, it would be one complete oscillation would be all the way down and then all the way back up. So that's one complete oscillation. And the time that takes is called period. Frequency is the amount of time, amount of oscillations per second. So this is actually the inverse of period. So T is actually equal to 1 over f, or if you like, f is equal to 1 over t. Now generally frequency has units of hertz, h is e, which is just a cycle per second, or an inverse second, or a 1 over second. Okay, but we are going to investigate that a little bit more in lab. The other thing we should be familiar with is a term called amplitude. Okay, and amplitude is maximum displacement. Maximum displacement from rest, and so, or from equilibrium, if you will. So what we have here, if this spring oscillates between these 2 points, its equilibrium position will be in the middle. So this is an amplitude and this is an amplitude. This whole thing is actually twice the amplitude. So those are some terms we're going to be using, some things we're going to be familiar with, and I think now you're actually ready to go ahead and start the lab.